Good afternoon, ladies and gentlemen, and welcome to this presentation. We are going to travel into virtual twin experiences dedicated to semiconductor. So first, Dassault System, we are the 3D experience company, and we are uniquely positioned to enable our customers and semiconductor companies create virtual twin experiences. So first we have a platform, the 3D experience platform, and with this platform you are able to combine modeling and simulation, science-based, data, and collaboration in order to create a product or a service experience. So we combine modeling and simulation to represent any product and services, systems and behavior. We use data from the real world to connect to that virtual model and to calibrate or to optimize that virtual model. And of course, we leverage collaboration services and applications in order to get things done faster. So this is about the 3D experience platform, and this is how we are able to apply these principles into semiconductors. So our strategy for semiconductor companies is based on three main pillars. The first one, I would call that the what, is the blue axis that is in the center. So this is about the device, and this is about how you can create a virtual twin experience of the device. Let's take the case of a sensor or of a MEMS, and you are able to represent completely accurately the device, and you are able to predict any behavior the device can have during its use. Okay? You can also take real-world data and input that data into the device in order to predict the future possible behavior of the device based on the data coming from the real world. So that's axis number one, the center one. And this is what I call the what. Now, the how. The how is on the right. It's the yellow axis, and this is all about the production means that is meant to be leveraged in order to produce the device. So we start from the materials, we go through the process, the wafer, the equipment, the clean room, or the fab. So this is about the how, and we are going to see that we can create a complete virtual representation of that ecosystem. And finally, the third axis is about the who, and that's the orange pillar on the left. And the who are the people, are the processes that are meant to be used and to be leveraged in order to create those virtual twins. So that's the virtual twin of the company or of the supply chain, the value chain. And those three pillars are based on one simple assumption, is that the world of semiconductor is changing. We knew the semiconductor value chain being global. Today, we are going local. We are going sovereign. We are going to the chip acts in the US. We are going to the chip acts in Europe. You are going, and so we need to accommodate these changes into the way we want to serve our customers. So another aspect of a virtual twin is that you do model, but you do also simulate. And by having that modeling and simulation loop, you make things get done quicker, faster, better. And for that, you need to have what we call a model-based data model. You need to have a repository where every aspect of the product, the service, is represented by a model. Why? Because models are what are going to be used for simulation. Let's now dive into small examples of this. And I'll start by IP design. IP design is important in semiconductor. And typically today, when we talk about IP design, we talk about IP management, IP reuse, and we talk about physical layout and design sign-off, verification and sign-off, okay? And you can see here you have IP management basically is in logical, and EDA design and integration for logical design and for layout design, and finally verification and design sign-off. But we have to understand that basically any design, any purpose has to address a requirement. And today, even if you think about the requirement that you should meet, you tend to go quickly from requirement to IP. What we are seeing and what we are basically enabling our customers to do is that there is a step in between. This step is you do not have to focus on the logical behavior of your design, of your chip, but you have first to understand what is the functional behavior you would like the system to get. And here, by doing so, you are going to focus on the high-level behavior rather than in the implementation of the IPs. So we provide a full end-to-end traceability from requirements to design sign-off. What this means? It means that if you need to change, if you need to rework, if you need to understand what is the impact of a defect that has been found later, so you have all the ability to understand the impact of that change and to take the most appropriate decisions to do so. Let's see this in action. What you see on the left side is an example of the way we manage IP management inside the platform. Okay, first we start by cataloging the IPs, making them available for reuse. Then after we create the system architecture, focusing on the function and the functional simulation. We can then link them to requirements and trace the design from the requirements up to the IP logical BOM. On the right side, what you see is our ability to converge quickly to a performance power area design sign-off. What this means is that we collect data coming from timing, power, and area. We dashboard this data and we interpret this data in a way to show trends and to give designers the options that they have to close as quickly as possible on design sign-off. Another example I would like to share with you today is the ability to enhance the way you collaborate on the device design. So here, what we are talking about is the ability to go from chips to the final product. And what you see here basically is that you can work between the end product OEM and the semiconductor company, the fabless or the IDM, okay? Instead of using SharePoint, mails, documents, files, okay? We use collaborative spaces in order to share and exchange. We use project planning in order to orchestrate the collaboration. We use requirements, objects, not files, in order to share the product specification. And finally, we define a systems architecture that can be shared. This system architecture can be encapsulated into a black box and shared with the OEM in order for the OEM to understand the behavior of what we are going to develop. And here, the handshake between OEM and semiconductor company can happen completely digitally. Okay? So at this point, the semiconductor fabless can start detail designing the design. The OEM can start coding, developing the software. And when the first prototypes, whether virtual or real, are ready to be shared with the OEM, so then the OEM can just apply the code on the prototype. Another example here is, so basically the idea to start with materials and process simulation at the molecular level, okay? So then you go and you go to the layout and you verify, simulate the layout. You do MEMS design and simulation. On top of that, packaging. And finally, you go to the customer and you take that chip and you port it to a printed circuit board. This, you have an end-to-end continuity. If changes are to happen, they can go as quickly as possible.
Thank you. So Manuel covered Dassault System Solutions for chips to systems and IP management on the 3D Experience platform for true end-to-end collaboration. Our lab to fab solutions are also changing the semiconductor industry with a focus on fab technology co-optimization, or FTCO. You may have heard of that acronym. So by leveraging virtual twins to model and simulate materials, processes, equipment, and the manufacturing environment, we are creating virtual test beds for innovation to flourish. So test beds are a hot topic right now in the CHIPS Act world. If you're familiar with what's going on with the Digital Twin Institute, the $53 billion allocated in the US for growing the semiconductor industry and manufacturing in particular. Test beds linking the public and the private, academia, government, into virtual environments where basically innovation can occur. That's a big focus of Dassault Systems and the solutions that we're presenting today. So our virtual twins can understand real-world data and learn how to modify process recipes to improve yield. And this is really the essence of FTCO. The beginning of this value chain starts with materials science. So we are going to do a deeper dive into materials with Nick Reynolds, and then I'll come back and talk a little bit more about our lab to fab strategy. Nick?
How do you? Okay. So yes, as John was saying, much of the work done in semiconductor development really comes down to materials. And often that is around the development of new materials, being able to predict the properties, understand the performance, how changing chemistry can ultimately affect performance of devices, and everything around the process of creating semiconductors and devices. So we provide capabilities around innovation of semiconductor materials. So understanding features such as surface chemistry, understanding processes like atomic layer deposition or chemical vapor deposition. And so understanding that chemistry, so organizations that create the chemicals, the materials that are used in these processes, make use of this technology to help drive innovation. Another area is around packaging and understanding the performance of polymers and other materials that are used in wafer packaging. We'll talk about the aspect of using these capabilities also for developing replacements for forever chemicals, so these PFAS materials, which are highly toxic, end up in the water and in soil, and so there's a big focus in how to use simulation to help drive the development of more sustainable materials, replacements that are less toxic. And we'll also talk about these capabilities around the laboratory, so to drive innovation more quickly in a more sustainable manner for managing the operations of the laboratory, experiments, how they're captured, how samples, materials are managed in a safe manner. So we talk about a virtual twin of semiconductor materials in simulation. So the top row here showing an example for atomic layer deposition. So understanding the chemistry. So at the atomistic level, being able to model the chemical processes that take place during ALD or chemical vapor deposition. So different organizations that make the materials that go into these systems use simulation to uncover what is the mechanism? How do these materials react? How do we form a stable, uniform layer on the wafer surface? And understanding that and understanding the kinetics of these reactions helps in the design. If you change the chemical structure, is that going to make this reaction occur more quickly, more slowly? How will it affect the stability of the product? And so those are all areas of research that are answered and informed by the use of this type of atomistic level simulation. In the area of packaging, so this lower curve here, basically a simulated stress strain curve where we have the packaging material, a cross-linked polymer mixture on top of the wafer layer, and then we're applying a stress strain simulation, so gradually delaminating it, pulling that layer off, and following the changes in stress to determine, okay, what is the deformation mechanism? Is it a simple delamination? Does the packaging material itself begin to fail on its own before delaminating? So this is used as a way of being able to screen different materials to be able to determine, okay, how will different polymers or other types of materials form this surface to help in the packaging and protect that. So these are things that can be modeled again to help drive experimentation, to be able to test things on the computer virtually before going into the laboratory. So using a more rational approach to the design. So this approach can be used to look at identifying replacements for these PFAS, so these perfluorinated alkyl silane materials, so forever chemicals. So the ability to predict properties like the aqueous solubility and being able to predict interaction with soil. So in this case, how these molecules interact with the clay layers in soil. So to be able to virtually screen different materials as well as new replacement opportunities. And it's also the ability to use generative design. So start with a basic structure, now use generative methods to generate a large library of potential chemicals and then be able to screen them. How will they bind to the soil surface? How water soluble will they be? How will they mix with other materials? And in this way, help drive experimentation. So apply simulation, so the virtual world, to help develop an understanding of how these materials work and help drive the selection of materials that actually would be tested in the laboratory. And then when we go to the laboratory, so having a more sustainable operation, so being able to manage, so rather than just entering information into a spreadsheet or a PDF file that gets thrown into SharePoint, but having a systematized way of centralizing how is experimental data captured. So people, analysts, technicians, engineers in the laboratory who are doing tests, they're designing samples. What are those samples made of? So having a record of what materials went into it, what supplier, lot. So there's traceability. If we develop samples and we do tests on them, you can know exactly what material, what supplier was used in that. And then having standard recipes or methods, which could be around preparation of samples or how they're tested. So that whole process of how these tests are executed, capturing that information in a standardized way such that it can be searched, leveraging past information in new studies, and then be able to organize that information to be able to apply machine learning. Again, using the real world to develop the data and develop information from that, being able to build models and then predict the performance of new untested structures. And so now I'd like to pass it back to John. Here.
Thank you. So the application of AI on these ever-growing databases of material properties and simulations is one of the key elements in the test bed strategy that we're going after. The semiconductor industry needs to find new materials to replace PFAS, for example, and this is a great way, so thanks, Nick, for sharing that. So our partnerships with leading stakeholders across the value chain are contributing to the emergence of semiconductor ecosystems. And they're being utilized, as I mentioned, by academia, by government, and it's the way that we're proposing with our platform strategy to connect multiple entities that would typically not be able to collaborate and innovate together. We are providing an environment for that to occur. So we're working closely with NIST and the U.S. Department of Commerce, and we're working with them to create virtual twin solutions, particularly the Digital Twin Institute you may be familiar with. There's a NOFO out there now, and there are proposals that are going to be supplied to NIST on September 9th. So we are a part of those consortiums and positioning the 3D Experience platform as the de facto standard for collaboration around these virtual test beds that I talk so much about. So in addition to the Digital Twin Institute, we are developing with many of our partners these platform test beds in order to advance research and also workforce development. You may have heard recently Deloitte estimated that there will be a deficit of 1 million skilled workers in the semiconductor industry by 2030, and our solutions are aimed to solve that problem. So our solutions can manage engineering BOMs, manufacturing BOMs, and bill of processes while maintaining digital continuity. So the video on your left kind of shows how that is managed within our platform. The video on the right shows the Purdue Burke Nanotechnology Center. We have a close partnership with Purdue University, and you can see that in addition to providing kind of a immersive environment of what the clean room looks like for new students, the capability of this enables the student to actually do research on the equipment at the molecular level, looking at plasma reactions, for example. And if you haven't already visited our booth, which is on this level on the far aisle, we have this particular demo available on an Apple Vision Pro headset, which is something worth taking a look at. It will be available for 30 minutes after this presentation, and then all day tomorrow if you have a time to stop by. So one thing I did want to mention here is everything that you see in these videos, or the video on the right, it's physics-based modeling. And so you can modify the models, you can simulate, you can do what-if analysis. So the fab itself at Purdue is modeled as physics-based, as well as all of the equipment and the processes that are running on the equipment. And so that is what creates a truly collaborative environment where research can be done across the stakeholder community. So there are many use cases for value chain collaboration using virtual twins. For example, we're partnered with Lam Research to combine our virtual twin modeling and simulation solutions with their Simulator 3D to tackle etch and deposition, process modeling, and optimization. And so again, this partnership is feeding into the FTCO strategy where the simulations are being fed real data from the equipment, and then the process recipes are being modified in real time. So not only can you go through learning cycles faster, but your time to yield increases significantly because of this. When you apply AI on top of this, the AI can actually make decisions at a much faster rate than humans. And so it exponentially accelerates the learning curve and time to market for semiconductor companies. So this is just one example of the many partnerships that we're forming. And we look forward to working with all of you and your companies. And if you have interest in the solutions that we just presented today, we would love to talk to you in more detail about them and understand your specific use cases. So we have about 10 minutes to take questions if there's any in the audience. We'd be happy to do that. Any questions? Okay, thank you so much for coming.
Question.
Oh. So I think the question's for you, Manuel, IP validation.
Yeah.
Can you elaborate on the IP validation use?
How is IP validated, I think is the question in the system.
Yeah, please, could you hear?
I don't think it's working yet.
Yeah. Yes, so okay, IP validation use case. So basically you have a specification. This specification translates into a set of requirements. On those requirements, you have test cases that are described. Test cases that are based on parameters. They are based on tools that are going to be used to verify the test case or to validate the test case. And so then after you have design data that are applied to the test case, certain versions, certain revision. And so then you have a flow that starts. We read the test case, we start the test execution, we go fetch the design data, we fire the validation tool, we execute the validation. So the validation tool can be one of ours, or it can be any third party, okay? So we execute the validation tool, we wait until the completion, we get the results, and we log and dashboard the results inside the platform. Based on the results, we automatically set the test case execution to pass, failed, or need attention. Okay, did I answer your question?
Yeah, thanks for explaining that, but how would the virtual twin thing play into this? What you explained seemed to be like a typical any IP verification.
It's not that typical because, so for example, I'll tell you, most of the customers I meet today, so that their first concern is they have test tools. They do run the execution, but the link to system requirements and to product requirements is not there. There is no link, there is no traceability. First. Second is if a test case, a test execution fails, so then they need to trace, for example, what is the root cause analysis. And for that, they need traceability. They need traceability to the block, to the sub-block. They need traceability to the functional architecture and to the logical architecture. So today, execution is partial, and traceability is very, very, very minimal. Okay, the fact that we associate modeling and simulation, and we have a very, very close loop between modeling and simulation, and of course the execution of the simulation, so that allows us to go faster, and when there needs to be analysis of the failure, so then the traceability helps debug, helps understand, identify, debug, and know the impact. Okay? Any other question? Okay.
I have a quick question. So you showed a video from, you said the Burke Center at Purdue. I think it's at Purdue University, right?
Purdue University.
How would someone in the audience that wanted to do something creative with Purdue, how would they leverage the power of a really smart university or smart people with our technology to innovate within their company? Like what is the methodology for getting started with something with Purdue?
Well, I mean, they could work with Purdue now. I think the bigger play is with the Digital Twin Institute that will be stood up in the first half of 2025. And that's really the test bed where companies, and the public sector can interface with the technology that we're developing now with Purdue University. If you're interested in working directly with Purdue, please contact me and I'd be happy to arrange a connection. Okay, thanks for the question. Any other questions? Great. Well, thanks for coming. Appreciate it.
Thank you.
Enjoy the rest of your evening.
Thank you.